All right. So one quick reminder, and then a couple comments about schedule. So the Stopper Lab report is due next time we meet. So for you guys, that will be Wednesday. And I'll try to give you about 5 minutes or so at the end of the period, just to touch base with your group and make sure everybody's got what you need to get those reports done. In terms of the schedule and the test you just took, I'm almost done grading them. I already had at least 2 people get perfect scores. So that surprised me that I've already just in the amount that I've finished, because I go page by page. So I'll probably finish them tonight and hopefully get them posted tomorrow sometime on Access. My goal is I've got a few students doing makeups on Wednesday, and I think after Wednesday everybody will be done. So I'm hoping Thursday for A Day and Friday for B Day we'll actually hand them back and go over them. But yeah, we'll talk more about that when I have them all graded and we can get them back to you. In terms of transitioning, we're starting Unit 4, and this is Unit 4 for us and also for College Board. This unit is really short, so we're going to finish it this week and next week, but not with enough time to take a test before ski week. So we're just going to do the unit this week and next week, finish it up, have ski week. I'll give you a few things that I would recommend that you do over ski week for like reviewing and preparing for the exam, but there won't be like a formal assignment. And then after ski week, we'll do Unit 5 on momentum. It's also short, about the same length, 2 weeks. And then we'll take a test on Units 4 and 5 combined. And then Unit 6 is simple harmonic motion. It's the shortest unit of the year. We'll probably cover it in about a week. And I don't think we'll do a separate test since it's just so short. And then we'll get into the last Unit 7, which is a little bit longer. It's not super long, but it's a little bit longer, and it's the hardest one of the semester. So we'll take our time and make sure we get that done, and we'll combine 6 and 7. So you'll have 2 more tests, one on Units 4 and 5 combined, one on Units 6 and 7 combined. And then we'll have, of course, our final exam. And your final exam will be a practice AP exam that we take in class before the actual May 13th date. So after May 13th, there won't be any more tests or exams. That kind of depends on what the school decides. Some years they've given a lot of freedom on what we can do. Other years,
I was going over some stuff with my English teacher.
Okay. Some years they've been a little more rigid on that, but we'll figure that out when we get a little bit closer. But after May 13th, we won't be covering anything you'll be tested on. All right?
Bye.
All right, so what we have today, we're going to talk about energy, work, and power just to introduce this new unit. We're going to talk about the little handouts that you picked up there and the pictures of spring chickens and pie charts. And so let's jump into that. All right, so most of you are probably going to have some familiarity with the terminology here. You'll maybe know quite a bit of it for some of you. We're going to talk about types of energy, and it says types of energy on the slide, and that's what most books call it. I think it's maybe a little bit more accurate to call it the storage modes of energy or modes of energy, because energy is just energy. It doesn't really come in different types, but most books refer to it that way. So if energy is kinetic or potential, it's all just energy. We measure it the same way, we evaluate it differently mathematically, but it's all just energy. So types, some books argue against that. I agree. I don't know that it's the best use of the term, but that's what most do say. So we'll stick with it for now. The first form that energy can be stored in is, we call it kinetic. So what do you know about kinetic energy already? Yeah, it's the energy of motion. So kinetic energy is the energy of motion. And there's a few ways we can abbreviate it. I usually just do KE. It makes sense to me. It's kinetic energy, KE, pretty easy. A lot of books and worksheets you might see will use E with a subscript K, just to show that it's energy that is kinetic. So also not very confusing. College Board chooses to just use K. It's a capital K. I'm not real fond of that choice because there's so many other uses of K in physics. It's the spring constant, it's the electric force constant. Now those are lowercase, but yeah, telling a lowercase versus an uppercase K is kind of tricky. So I'm not a fan of it, but that's what they use. And the equation for it, and they do give you this on the handout, is 1/2 mv squared. So that is the equation that is on the College Board formula sheet. And so what is kinetic energy based on mathematically?
Mass and velocity.
The mass of the object and the velocity of the object. And which one carries more mathematical weight in determining the energy?
Velocity.
Yeah, velocity is squared, right? So,
velocity?
all right, so that is kinetic energy, the energy of motion. We know it's got motion because it has to have velocity to have kinetic energy. If the velocity is 0, there is no kinetic energy. So it has to have velocity, it has to have motion to be kinetic. Now for potential energy, there's multiple forms of potential energy, multiple ways energy can be stored as potential. We're going to use 2 in this course. I'm going to mention the other 2 briefly, but we'll start with the ones we'll use. The first one I'm sure you've heard of, gravitational potential energy. So what do you think it's based on?
Gravity,
Gravity. And what's gravity based on?
mass, and acceleration.
Yeah, mass, acceleration, distance. We've got a few things there, but mass is, when we think about the basic part of the gravitational formula, it's mass 1 times mass 2, right? So we know the mass is a big factor. All right. Now, with gravitational potential energy, I generally just abbreviate it with like an acronym, GPE. And that's pretty common in a lot of different books as well. But College Board uses also a fairly traditional, I don't have any problem with this one at all. They use UG. When you see capital U, that is kind of the standard abbreviation for any potential energy. And so that means potential energy that is gravitational. So that's pretty standard. And then they give the equation, M, like we said, it needs mass to have it. G, it's based on the gravitational force field of the Earth. And then I usually write H for height, but they actually don't use H, so let me change it.
You just use delta Y?
They use delta Y, which is easy enough. But that's how they have it on the formula sheet. All right. So a quick example, if I were to store a bowling ball, we have some back there, and I have them all stored on the bottom shelf because that means they have very low potential energy. If they fall off the bottom shelf, they're falling a couple inches and not going to do a lot of damage, not going to cause a lot of change in anything, right? If I stored them on the top shelf and we had an earthquake or something and they fell off, they would do a lot more damage. The mass would be the same either case, the gravity would be the same either case, but the change in height gives them more or less energy. So we store the bowling balls on the bottom shelf so that they do less damage if they fall off. We want to have low potential energy so they don't damage the floor if they happen to fall off the shelf. All right, the other kind of potential energy that we do need to know about for this course is elastic potential energy. Anything that can stretch or compress. So rubber bands, springs, those like super balls that bounce real high.
So when you have a projectile being launched by a slingshot, talking about the projectile, is that elastic potential energy?
Yes. So the projectile is launched using elastic potential energy, and that elastic potential energy, when it's launched, converts to kinetic.
Okay.
So when you pull back the slingshot, you're storing elastic potential energy in it, and then when you let go, that stored energy converts to kinetic.
Will they be equal?
Yes.
Well,
Yes.
initially, because we also
Yeah.
have to factor in stuff like air resistance.
Right.
The idea is once it leaves the slingshot, the kinetic energy and the elastic potential energy should theoretically be equal.
Correct. That is correct. And that's how we often solve problems, is making connections like that. Like, I stored it this way, now it's kinetic, those two should be equal, and so then I can solve the problem. Now, elastic potential energy, I again just usually follow the traditional acronym form. It's just EPE, but College Board uses also a very traditional form, US. U for potential energy, S for spring, which makes it a little more, sound is like a little more specific, but anything that can compress or stretch could be considered some sort of a spring.
Or another way to write it down would be UEL.
I have seen that as well, but this is how College Board writes it.
Or at least E_EL is what you have on the worksheet.
Mm-hmm.
Is that still elastic or is that electric?
No, that's elastic. We're going to mention electric, but we're not going to learn about electric. So.
Is K, what's K gonna be there?
Spring constant.
Yeah, that's the spring constant, good. So a lot of times students see that and they think, is that kinetic energy? Because we're talking about energy right now, but it's not kinetic, it is the spring constant. So what's the X?
Delta X?
The change in the spring's length, or, like you guys did the Hooke's Law lab, right? Where we reviewed this equation, spring force equals Kx. And you hung different weights of force, creating the force on the spring, measured how far they stretched, and then you graph to find the K value, you graph to find the spring constant. It's the same variables here. We're actually gonna derive the 1/2 mv squared and see where that comes from. We're gonna derive the 1/2 kx squared and see why is there a half, why are we squaring these things?
So, I guess like, to kind of put that in context, so when we derive our delta X, so in equation, let's say, it's an aircraft carrier that's, gonna help propel a plane into the air.
Mhm.
So, let's say, I don't really know how long they're gonna be, so let's say, from the place where the plane is connected to the, let's say the sling, to the front tip of the aircraft carrier is 50 feet, would our delta X be 50?
Right. You'd probably want to use it in meters or whatever. It depends on what the
Yeah,
K value
measure
is,
the
but
SI
yeah,
units.
yeah, right. Yep.
Cool.
All right, so those are the forms of energy that you need to be able to calculate, and the 3 equations that College Board gives you. They do also give you this spring equation for Hooke's Law. It's just not an energy equation, but they do have that. We've used that before, and it is on the formula sheet. Now, the other 2 types of potential energy, I'm just mentioning them because they're not part of AP1. So I just want to mention them, but you don't have to know them. We're not going to look at any equations. So that's why I've put them as a different color. So electric potential energy is based on the charge, not the mass of the objects. And we've learned about electric force, so it makes sense that if there's force, then we should be able to store energy. And we can, but it used to be introduced in AP1 and then fleshed out in AP2. Now it's just entirely moved to AP2. So this is one that they have confirmed clearly. There will be nothing about electrical potential energy on the exam for AP1. So that will not be covered. Electric force is still a little hazy, whether that's going to be on there or not, but electric potential energy for sure not. The other one, for those of you that have had chemistry, if you drew bar graphs for energy in chemistry class before, you've talked about chemical potential energy, the energy stored in the bonds of molecules. And so breaking and making those bonds, if you use Hess's law and evaluate the enthalpy and the entropy and Gibbs free energy and all that good stuff. So that is, again, something that we leave for chemistry and don't cover in this course. And now the last one, let me give you an example here first, and then it'll maybe make sense of the last one. So if I have this ball, and let's ignore, it is compressible a little bit because it's soft, but let's ignore that. Let's just think about it as a solid sphere. If I just hold it right now, what kind of energy is it? It has what kind of potential?
Gravitational potential energy.
Gravitational potential. Now if I drop it, what happens to that gravitational potential energy?
It turns into kinetic energy.
It becomes kinetic. So if I have 10 joules, I'm just making up a number. If I have 10 joules of gravitational potential energy, how many joules will it have when it gets to the bottom? Still 10 joules. And that's the conservation of energy principle that we're going to talk about later this week. But if it starts with 10 joules of energy, it has to end with 10 joules of energy. But it's all gravitational here. What about right down here when it reaches the ground? Yeah, it's all kinetic at that point because it's 0 height, but it's maximum speed, right? Here it's maximum height, 0 speed. And so if this would be 10 gravitational, 0 kinetic, and then 9 and 1, and then 8 and 2, and 7 and 3, and on down, halfway be 5 and 5, right? And then right as it hits, it's 0 gravitational because it has no height anymore, but maximum speed, so 10 in kinetic. Now, if that's perfectly true, if I drop it from this high, how high should it bounce back up? Should bounce up to this high again, right? Like if I don't lose any energy, but does it? No. So in reality, we know that energy should be conserved, but in reality, in certain scenarios, it's not very well conserved. And so we have to introduce a last concept here called dissipated or thermal energy. I prefer the term dissipated because it's more broad. What do you think thermal is referring to specifically?
Heat.
Heat, yeah. So a lot of time dissipated energy is heat from friction, air resistance. It heats up the air particles as it moves through and bumps into them, makes them move faster.
Yeah, but isn't heat just another way of describing energy?
Well, heat is a specific kind or form of energy storage. It's stored in the movement of the particles. It's actually a type of kinetic energy, but it's a byproduct of, like, when I drop the ball through, it's pushing air particles out of the way. And temperature is just the average kinetic energy of the particles. So if it's pushing them out of the way, all those particles are going to be now moving faster than they were.
Yeah.
So they've got a higher kinetic energy, therefore a higher temperature. So the thermal energy that gets changed in the environment as something moves could be thermal because of increasing the particles' movements. But it could just be like when the ball hits the ground, you hear it, right? Your eyes closed, you know when it hits the ground because you can hear it hit the ground. And that's sound vibrations, which is another form of energy. So the dissipated energy is a little more general. It could be the thermal heat by making the particles move faster. It could be the sound vibrations that go off as sound waves. So dissipate is a little more general, thermal is a little more specific, but to be honest, a lot of physics books don't use the word dissipated. They just call everything thermal, even though it's not always just thermal. So I just prefer this term. College Board kind of goes back and forth. There's a variety of different ways that you'll see it represented. Sometimes you'll see it as UTH, which seems weird to me because it's a little bit odd to think about it as potential energy if it's causing the particles to move faster, but and then more often I've seen it ETH, which that's fine, but it does mean we're assuming that it's thermal, or we're just counting thermal as everything, like not limiting thermal to just heat. So the abbreviation that I think makes the most sense is just E with a subscript D, because then it's energy that's dissipated however it's lost. If it's lost as heat, if it's lost as sound, whatever. The College Board usually just uses the words. They'll usually just say how much energy was lost, or how much energy was dissipated, or how much thermal energy. If it's all friction, it's mostly thermal. Yeah, Griffin?
Does it, like, would they mark us off if we used a different one than they typically?
No, all of these variables are considered standard variables to use. So if I would just encourage you to get used to using the ones that they give you, but if you use a different one that's a standard, or you put a key off to the side that lets them know what you mean by it, that's always fine.
However, it'd be wise to know the ones they use, because they'll probably be what they ask for on the test, if they ask for it by name.
Yeah, and if they said kinetic energy and you wrote KE, they wouldn't count off, it'd be fine. But when you're looking for it, it's just K. So it's more like, oh, I need to know where to look on here to figure out what it is. So I use the right equation. To me, that's kind of the more important thing, because all the teachers that grade these are physics teachers. And so if someone puts KE, GPE, EPE, those are in hundreds of physics books. So we all know what that means. We're not going to get confused by that. Now, if you used like Z, we might, what are they talking about with Z? But if you made a key off to the side and said, I'm using Z to represent this or whatever, that's fine. We can figure that out.
Yeah.
All right. Any questions about these storage modes of energy? All right. So the last thing I want to talk about here is I got these little toy spring chicken things.
Chicken.
You guys probably have seen little toys like these before.
Oh, he's moving.
So you guys have probably had toys like this, springs, you put them down, they fly through the air. So we got this spring chicken. And this one, the purple one always seems to stick there longer. It's kind of like picture A right now, over there in the picture, right? So what kind of energy does it have?
Potential.
And what kind of potential?
Gravitational. Actually,
Elastic.
well, it's
Yeah,
springs, so
elastic.
elastic, yeah.
Yeah. Now, just for simplicity's sake, I know that all three of those fell down to the ground because it's just on a little corner of the table. But let's assume this was on a really big table where when it comes back down, it's going to land on the table again. Maybe this one will because it's a little bit farther from the edge. So right now it's all elastic potential energy, and it's at zero height if we're considering the table to sort of be our zero level. And it's not moving till now. So At the beginning, it's all elastic. At the end, when it's just laying on its side, what could we say? All of this elastic, what happened to it?
It's gone, well, it's been used up, and then it was then turned into gravitational. However, when it's laying down on its side, I would say it has no energy?
What do you think?
Would it be GPE?
Well, GPE is based on height, so where would it have a lot of GPE?
What's in that?
Like E.
D.
Yeah, D, if it's at its maximum height, that's gonna have the highest GPE, right?
Yeah.
Would it have any velocity at the peak?
No.
Not at the peak. And the spring is no longer compressed or stretched, so at that point, it would just be GPE, right? But what about at the end? It's just like laying there.
Oh, dissipating.
Dissipated, yeah, all that energy, whatever it used to be, it's just all been lost to the environment through the air friction, through the sound when it hit the table, through the, the vibrations in the table. Just all been lost to the environment. Now, what about C?
Kinetic, because it's in motion and the spring is no longer having an effect on what's happening because it's already extended completely.
Got that for sure?
And
Would it also be dissipated?
Possibly. If there's any air resistance, we could say there's some dissipated, or if we say, well, the air resistance is negligible,
Well,
we could say it's still gonna have something else,
GPE?
GPE,
yeah,
because it's got height.
well, then we can also infer that there's another force acting upon it because the arrows are different in size.
Yeah, so here, I don't know if they're using that for the arrows. I think the arrows here just represent velocity. That here, that's maximum velocity, and here it's less.
Mhm.
So with some velocity still, we could say, yeah, there is some kinetic energy. I'm gonna just do it this way. We don't know the exact percent. It looks like it's a little bit past halfway though, so I'm gonna say it's a little bit more gravitational potential and a little bit less kinetic. Now, you could say it's half and half. You could say it's 75-25, 60-40, 70-30. There's not enough information given to really be precise. But we know it's gonna for sure have those two. If we say there is air resistance, then we could add a little sliver here and just say, there is a little bit of dissipated energy. If we wanted to count air resistance, we could do that. The tricky part of doing that is if we count air resistance there, then we have to make sure because the dissipated energy, once it's lost, it's lost. So it would have to carry through, and it would just keep getting bigger and bigger. So while we could do that, I'm gonna erase it for now, just to make it a little bit more of a simple approach for this first example. So what about E?
Reverse, would it be the same, but like with reverse, percentages?
So would it be reversed?
No.
Griffin, what do you think?
no, it'd be the same. It's just the direction of the velocity is different.
Yeah, so same height, therefore same gravitational, same velocity, just different directions. So that's gonna be identical. So however you drew, I didn't do that very consistently there, so I can fix that. However you draw C, you wanna try to draw E to be the same, right? So just a little bit off for me. It's gonna basically be identical. Again, if we're ignoring air resistance. What about B and F? Still touching the ground.
So it would just be potential, or,
No,
no, because it's not being
What do you think,
acted upon
Jack?
by gravity,
like,
it's just.
kinetic.
Kinetic, yeah. If it's on the ground, there's no GPE. The spring's already launched, so there's no EPE, but it's got maximum velocity, so kinetic energy. How about F?
Same thing.
Same thing. The velocity is opposite direction, but it's the same amount. No height, no spring, all movement, maximum velocity. The mass never changes, so that stays constant throughout. It's just, what about the velocity? What about the spring? What about the height? All right, so that's our quick analysis of spring, chickens, and pie chart. All right, so on your way out, make sure you do touch base with your lab partners and make sure you all have what you need to turn in your lab report, because it is due next time, but that's all we have time for together today. So touch base with your partners and then enjoy the rest of your day.
I've got everything.
Griffin just giving me his phone number.
Are you good on the lot?
You good?
Do you have everything you
Yeah, I know
need?
where he is.
And then Griffin's good.
I'm out of here.
You're not staying,